So we've been talking about integrals lately, and we've been talking about two different kinds of integrals, definite integrals and indefinite integrals. Definite integrals were when we were trying to solve the area problem, finding the area between some curve and the x-axis bounded by two vertical lines. So kind of a geometry problem. And the indefinite integral was the process of finding an antiderivative to the function. That is, asking ourselves for some function, what kind of function would have this as its derivative? So that's really tied to the slope problem, which is really a very algebraic problem. So you may have wondered why these two very different processes have such similar names, definite integral and indefinite integral. And the answer to that is what we're going to talk about in this video, which is the fundamental theorem of calculus, which says that these two processes are very tightly aligned, and therefore differentiation and integration, the two subjects of calculus, are also very closely entwined. Let's take a look at the fundamental theorem of calculus right now. There are actually two different forms of the fundamental theorem of calculus, and some people call them part one and part two. Some people call it the first fundamental theorem of calculus and the second fundamental theorem of calculus. For various historical reasons, we introduce them to students in the opposite order. So this is the part two of the fundamental theorem of calculus. All right, so if f is continuous over some interval, all right, so I've got my function, and here's my a, and here's my b, and I've got some function f that's continuous. It's well defined between these 2 points. So therefore, I can talk about the definite integral of f of x dx from a to b, which is the area of that shape. All right. All right, and going on reading further, if big F of x is any antiderivative of f of x. Remember, an antiderivative, when we were thinking about, say, the antiderivative of 2x dx, remember we were very careful to say x squared plus some constant c, because any constant at the end of x squared would give us 2x as a derivative. But here, this is saying that f of x is any antiderivative. So usually when we're thinking about this, we will take f of x to be the one where c is equal to 0. You'll see soon enough that this is okay, that it doesn't matter that we would be using, it doesn't matter which function we use as the antiderivative. All right, f of x is any antiderivative of little f of x, then this says that the area of f of x dx, this area, is equal to big F of b minus big F of A. All right, and one way that you will often see this written is F with A and B. So it's got the same limits. I don't even know what we call this symbol, but it's just kind of a quick and dirty way of saying to calculate this definite integral, we just need to evaluate any antiderivative at B and A and then subtract them. Okay, and like much of calculus, we are not going to bother proving this. But what we will do is we're going to go through this notes packet, and we're going to see the antiderivative for functions where it's very easy to calculate the shape. So we're not going to have any trouble doing that. And so we can see for those simple cases that the fundamental theorem of calculus kind of checks out on those simple functions, and then we can just trust that it works in the rest of the cases. So that was the second part of the fundamental theorem of calculus, which is going to be a really important part of our ability to actually calculate these areas without doing Riemann sums, which saves us a lot of calculation, and it will also give us a precise result instead of just an estimate. So big win. Thank you, fundamental theorem of calculus.